All right, in this video, we're going to talk about atomic emission. So at this point in the course, you are probably watching these lecture videos on atomic absorption and atomic emission. And it seems like everything that we've done, even outside of this course, has been atomic absorption. Anytime we've went over to this instrument, it's always been AA that has mainly been the focus. But in this particular lab experiment, it's not really kind of sample processing. It's just really an introduction to how atomic emission works. That's really all that it is. Very similar to the very first atomic absorption lab that we do, where we run copper standards and we run them at primary and secondary and tertiary wavelengths. There's no really sample, so to speak, that goes along with those particular types of labs. It is just the basics of the understanding of the instrument and how to get it to set up to do the emission part in this case, and not the absorption part. So in this particular experiment, we're going to be focused on atomic emission of sodium. And sodium, of course, is the elemental symbol of Na. So we all know that, I hope, at least most of us do. And that sodium is a very distinguished sodium emission line. So keep in mind, polarimeters have sodium D lamps, and refractive index instruments or refractometers have sodium D lamps. So sodium is a very quick go-to, very good general introduction to what emission is all about. So what you're seeing here on the first page of your lab document is this difference between the atomic emission of sodium and the atomic absorption of sodium. So they are the yin and yang of the visible spectroscopy world, right? And I'm saying visible because very often these wavelengths are in the visible realm. Not every single time, but very often they're in the visible realm here. So what you're seeing up here at the very top is the AA, the atomic absorption. And as you can see, all of the rainbow of colors, R, O, Y, G, B, I, V, all of those are present except for a tiny little sliver that's right here, and that is a dark line, and that's what we would call maybe some of these Fraunhofer lines. These are areas where the color is not continuously showing up. It is an area that the atom or the compound actually absorbs. And in our particular case with atomic absorption and atomic emission, we are mainly focused on metals. That's what we're really focused on. So down here at the very bottom is the AE, and the AE portion is the emission. So what it absorbs, it has to spit out, and that is the emission section of what we do here with these instruments. So sodium D is used because very often it's very clean. There's not a lot of different emission bands that show up with sodium. And when compared to some of the other choices, this is our best, cleanest choice that's out there. And it also is pretty reliable and pretty cheap. So why not use it? And that's what they've decided to do. And then in this lab, we're using sodium for the same reason. It is a very simplistic emission spectra that it gives. It's just mainly one line, and that's the sodium D line. And that's what we're going to measure, and that's what we're going to pick up. And that's basically how we're going to set our machines up. All right, so as I scroll through the lab experiment, you're going to see standard preparation on the very first page of the data sheet. And depending on how many people's in the class and how we decide to divide this up, what you will find is that a set of standards are going to be required, and they go very low. So 0 just means blank, and the blank in this case is just our solvent, and that solvent's going to be water. And then we go 2, 4, 6, 8, 10, and then 20, 40, 60, 80, and 100. So we have a very wide range of emission here, and we're doing that on purpose because you're going to see that later on in the procedure about why we do what we do because of the standard preps that we've chosen. Up here at the very top of the table, you're going to see that our higher standards, our 10 to 100, are going to be made with 1,000 ppm solution. So the reason for that is because they are higher concentrations, and higher concentrations that are needed to be prepped require higher concentrations that are much higher than them, of course, right? So this is just simply going to be our traditional CV equals CV equation, just the dilution equation. That's all that we're needing. And it says I need to make a 100 part per million. I need to do 100 milliliters of those, and I'm going to use a 1,000 ppm in order to make it. Quite honestly, I might tell you to change this. I might tell you to do 50 instead, and that's something that I'll tell you in class when we get to there that day. And the reason is because we might actually get someone else to make 100, or we might duplicate on the 100, and that 100 can be used to make everything else with, because as you can see down here, we switch, and that switch is going to happen at our lower concentration. So we make a 100, and then we use the 100 in order to make the 8, 6, 4, 2, and 0. In addition to that, there is a chance that I will make 100, and you will not need to make that much of a 100, whoever does the standard prep. So because of that, we will have extra, we will have excess, and there's no need to make a 100. We'll make a 50 instead. So it really just depends on the classroom, that particular year, and so forth, but you'll find that out the day of the lab experiment. So I'm going to stick to the plan, and I'm going to basically look at this and just pretend, okay, I was told to make a 100 mils of a 100 ppm. So my initial concentration is going to be 1,000, because that's what I'm starting with, and I don't know how much of that to use. I want to end up with a 100 ppm, and I want to make 100 of that. So with that said, I mean, that's going to be a very quick calculation. You could probably do that into your head. If not, here's a calculator on the screen, and we'll take 100 and we'll multiply by 100, and we'll hit equal, and that will give us 10,000. And then we'll take 1,000 times x, and the opposite of times is multiplication, or division. So we will divide by 1,000 here. So when we do that, we're going to see, okay, we'll need 10 milliliters in order to make that particular standard width. So x is going to be 10 mils. So I need 10 mils of a 1,000 ppm solution. I need to put that into a 100 ml volumetric flask and dilute to the line with water, and that will make a 100 ppm. All of the other standards are going to be the same way. So for instance, down here in the very bottom, okay, I'll do CV equals CV, and we will start here with a 100, and I don't know how much of that to use. That's what I'm trying to find out. And I need a concentration of a 8, because that's what the table tells me to make. And in this case, I need 50 milliliters in total. So again, I'll just do the same thing once more. You maybe can do it in your head, but if not, I'll pull up the calculator so you can follow through with it. And here we're going to take 8, and we're going to multiply by 50, and that will give us 400. So 100 times x. So the opposite of multiplication is division, and we're going to divide by 100 in order to get x by itself. So when we divide by 100, I'll hit equal, and we get a concentration of 4. Or a volume of 4, sorry. So x is equal to 4 milliliters. So I will take 4 milliliters of a 100 ppm, I will put it into a volumetric flask, and I'll take it to the line in order to get a 8 part per million standard. All right, so in summary, what's going to happen is that the class, or the cohort of people that will be doing this lab, will break these concentrations up. You will not be responsible to make all of these on your own. So we will divide and conquer with this table, and we'll have all of these samples that are prepped, and we feel really good about it. And then we move on into the procedure part. So procedure in step number 1 says make the standards as stated in the table. So we just did that. Check. Number 2, it says you'll need to make a quality control sample using sodium chloride salt. The sodium contributes 39.34% of the mass for the sodium chloride, Measure 0.1500 grams of sodium chloride salt, record the actual mass that you use, and dissolve the salt in 250 ml volumetric flask. Using a volumetric pipette, dilute 10 ml of this solution to 100 and calculate the actual concentration of the solution in terms of ppm. What? What on earth is he talking about? Okay, well, I promise you this is not very complicated. This goes back to traditional 150, CTC 150 standards and solutions, because this is a standard that we are making, and we're making the standard from a salt. That is how this is going to be a little different. So we are measuring out a certain amount of salt. We are dissolving it in water. We are breaking up the sodium and freeing that up. And that sodium is present in that solution, and therefore we know how much should be in that solution, and we're going to be running that in that solution. So that is what we would call the quality control check or the quality control sample. So the way that we prep this here, it tells us we need to measure out 0.1500 grams. All right, so 0.1500 grams. Let's say that we did this just straight out and it became even and it was 0.1500 grams. That's great. I'll write it here on the blank. I'll go through an example calculation for you, but there is a chance that this was not done. There is a chance that your number would be a little bit lower or a little bit higher, 149 something or 151 something. That really just depends on you and what you measure out and what you do for that particular type of thing. And that's okay. No one says it's got to be perfect. Just track it. That's all that you need to do. So I'm going to pretend I was perfect, even though I'm not. And then I will measure out 0.1500 grams. It says the actual milligrams of sodium chloride. Well, in order to go from gram to milligram, we're going to multiply by 1,000, and 0.1500 times 1,000, I move the decimal over 3 times. 0.150 is actually 150 milligrams here that we have weighed out to make this solution with. Next, it says, okay, well, what's the actual milligram of sodium? Because keep in mind, this 150 milligrams is sodium chloride. So chloride brings extra mass to the table. So therefore, we're going to have to use a percentage, and this is sodium chloride, NaCl. So sodium is like 22.99 or something. Maybe I can't remember right off the bat. Chlorine is 35.45. So there that goes. We're going to add those up. We're going to get a total, and then we're going to take sodium's mass and we're going to divide it by the total mass in order to get a percent of sodium. The reason I don't care what these actual numbers are is because it tells you right up there in the top what those numbers are going to be, and it actually works out the equation for you. It says that sodium in sodium chloride is 39.34%, and the way that we get this is that we take the mass of sodium, which was 22.99, and we divide by the total formula weight of sodium chloride, because that's what we're using. And that 22.99 divided by 58.44 times 100 is 39.34%. All right, so I'm going to bring my calculator up, and I know that if I measured out 0.1500 grams of sodium chloride exactly to the T, that's what I've got, I know now that only 39.34% of that mass is actually sodium. That is it. Nothing more, nothing less. 39.34% based on the percent composition calculation. So what we'll do is that we will multiply this by 0.3934. Now, if you've got a cheapo calculator from your phone, then it probably has a percent key. And you could have done 0.15 times 39.34 with percent key after it and hit equal. So it would have told you that number already, and you wouldn't have to convert it over to a decimal. But because this calculator on my screen does not have a percent key, and because my calculator on my TI-83 or 84 or whatever kind of version you have does not have a percent key on the keypad, then you've got to convert those into a decimal to do some math with them. So this means that if I weigh out 0.15 grams of sodium chloride, that is 150 milligrams. Out of that 150 milligrams, I'm only going to get a very tiny fraction of sodium. and it's 39.34%. So 0.15 is actually the number for gram, and this would be 0.059 gram, all right? So you can do it that way. Or because the question says the actual milligrams of sodium, I probably need to use milligrams instead. So I'm going to take 150, and then I'm going to multiply that because it's 150 milligrams. Then I'm going to multiply that by 0.3934 because that is the percent of sodium in sodium chloride, and I get 59.01. It just saves you an extra conversion step. That's all that it does. I would have been okay with the other route that we did first, 0.15, but 0.05 was gram, and this question required milligrams of sodium, so I would have to make that conversion changing gram to milligram. But here was a direct calculation: 150 milligrams times 39.34%, and that will give us 59.01 milligrams. Next up, it says, okay, now calculate the concentration. So if you took that 59.01 milligrams, the directions say take that amount and dissolve it in 250 mils of water. And it says calculate the concentration in ppm. So ppm means milligram per liter, right? That's what that unit is supposed to represent. I just calculated how much sodium is swimming in my solution, and that was in terms of milligram. I just did that. It's 59.01 milligrams, and we are dissolving that in 250 milliliters of water. Well, ppm requires liter, not milliliter. And what we have in the problem here in our sample prep is 250 milliliters. So I'm going to take 250 divided by 1,000. So 250 milliliters is 0.250 liters. So I'm going to bring the calculator up again, and I'm going to do this simple little calculation over here to the right-hand side. I'm going to take the number of milligrams of sodium that we have measured, that we have dissolved in a little bit of water. That's how much there's going to be there of sodium, 59.01 milligrams. And I'm going to divide that by 0.250 because I've dissolved that in 250 mils of water in a volumetric flask. So my concentration here in terms of part per million is 236.04. All right, so 236.04. Next up, it says, okay, now calculate the concentration because there is a dilution step that's required after this. And that dilution step says, using a volumetric pipette, dilute 10 milliliters of that solution that you just made to a 100 milliliter in total. Not a big deal. It's a dilution. So CV is equal to CV. So the concentration that I'm starting with is 236.04 based on my measurements, based on what I weighed out, based on the example that we're going by. And we have taken 10 milliliters of that solution and we have diluted that to a total of 100 milliliters as a final volume. So there's the setup for the dilution equation, and I need to solve for x, and x will be the concentration after this dilution takes place. So I'm going to take 236.04, and I'm going to multiply by 10, because that's what it tells me to do, and then I hit equal. And then that is 100 times x, so the opposite of multiplication is division. So I'm going to divide by 100 on each side. So here I'm going to divide by 100, and then I hit equal. And this gives me 23.60. All right, so 23.60 is going to be my, let me pull that back up. Is going to be 23.60 is the diluted concentration of the quality control check that I have measured, all right, or that I have prepared. Number 3, it says set the 100 ppm solution to read 1, and then read everything, every bit of it. And then number 3 again, because there's 2 3s for some strange reason, says set the 10 ppm solution to read 1. And then read everything that's below 10. So the 8, the 6, the 4, the 2, and the 0, of course. All right. Okay, so I want to talk a little bit about this before we go a little bit further into the lab procedure. So whenever we set up sodium emission, there are some things that I need to mention. And whenever we do atomic emission, when we set the instrument up, so I want you to go back and think about the copper linearity lab, if you've done that already, or if you've looked at other atomic absorption labs. The very first thing that we do, of course, is set the lamp, and we have to align it, right? So what goes on here is that there is no lamp for AE. No, there's no lamp at all. And the reason that there's no lamp is because we're working off of emission, because it's called atomic emission, and that's why sodium is going to give off what it gives off. So normally what would happen is that we choose a lamp, we plug the lamp into the port, we make sure the wavelength matches, we make sure the voltage matches, we make sure the slit width matches. We go through and we turn the screws so that way we can make the lamp go up and down and left and right, and we try to max out that green meter to max out the absorbance, because that is the way that we ensure that everything from the lamp is getting to the detector. With atomic emission, we do not do that, and the reason is because we don't have a lamp. That's the difference. So no lamp involved with atomic emission, and that's great because that's less that I've got to prep. Number two, what normally would happen is that you would look at maybe a cookbook. Hello, you would look at a cookbook, and you would make sure that your samples, your standards, have the proper wavelength. Wavelength is still important, ladies and gentlemen. Waves. It's all spectroscopy. So the difference here is that under atomic absorption, you would see multiple wavelengths, and it would be like, this is the best one, this is the most sensitive, this is the secondary, this is the tertiary, blah, 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 blah. All right, well, we're not using a lamp, so why do we need to be concerned with it? And that's because poor little sodium is getting ready to go into a flame, and it's getting ready to burn, and we're getting ready to destroy it. Oh no, sodium, I'm so sorry. Well, when sodium goes into that flame, it screams, and it screams wavelength, and we need to pick that wavelength up by the detector. So if we can tune in the detector to the wavelength that we need for it to look for, then that detector can do its job much better, and it can look for sodium only. And when it sees that wavelength escaping and screaming out by these burning little sodium atoms, then we will be able to pick that up on a computer screen and within the software and in terms of absorbance. So we still have to go to a cookbook, we still have to go to Lambda Max, and we still have to go to slit. And the reason is because these are really for monochromator pieces. They're not necessarily meant for the lamp pieces. So we are not using a lamp. We don't have to double check wavelengths and slit width and things on the particular lamp that we're using because there's not one installed. Instead, what we're doing is that we are double checking the wavelength and the slit width for the monochromator. That is what's built into the software for atomic emission. And once we do that, we are fine-tuning the eyeballs of the machine to see certain things. And now it knows I need to see sodium. So the cookbook will provide these, and whenever you choose the atomic emission in the software, like it does with the lamps, it will just automatically, most of the time, pull in the proper lambda and the proper slit width that it needs in order to measure that particular atom width or that particular metal, in this case with atomic absorption. So there are numbers that we still have to kind of pay attention to, and we want to make sure that we record those numbers down because I believe the data sheet is going to end up asking for it. All right. So if I'm not mistaken, let me see. If not, it will be added. So I'm not going to kind of waste your time more in the video right now. We'll see it if it comes up a little bit later. But if it does not ask for the wavelength and the slit width, you will see blanks that will happen there for you to record that data. All right. Okay, so now that we have this thing set for atomic emission, what's going to happen is that we will tune the machine, and I use that term very freely because tuning is really in reference to another instrument called a mass spectrometer, but we are somewhat tuning it for sodium. We want for it to see sodium and sodium only, but we have a really wide window of concentrations that we've made with our standards. So this is going to tell you that up front, you're going to start with your 100 ppm standard. And that 100 ppm standard is going to be used to tune or set the instrument. And what it does is that it sets that to be a 1 absorbance. We've talked about absorbances. We've talked about this idea that we have a working range, and that working range should be like nothing lower than 0.2 and nothing greater than 1.5. So the AA and the AE instrument knows this because it's very similar. And it's like, I don't want to go all the way to 1.5 because there is a chance that maybe some of your samples or some of your standards might run over 1.5, and that's not really a legit number. We don't like to be in those upper realms if we can do away with it. So the AE and the AA system, for us at least with Agilent, will take your high standard in the emission world, and it will adjust the detector setting for it to read that high standard as a 1 absorbance, and that's what we're doing here. So it's a comparison, right? So if this is my 100 ppm, and if I'm pumping that 100 ppm through the flame and the detector sees it, we don't want to overwhelm the detector. So what it does is that it looks at the signal that it sees and it adjusts itself. It will scale itself up or it will scale itself down in order for that standard to read a 1 absorbance. All right, so that's very important. So once it reads a 100 or a 1 absorbance, then at that time we can run samples, right? And those, whoa, that's real country, isn't it? And those samples will include the 100 ppm standard again. So number 1, we are going to set the instrument with the high standard, and I'm going to put in parentheses, ABS is equal to a 1 here in this case. Second, what then happens is that the machine will tell you, okay, I'm ready for your samples. So let's start running them. We are going to rerun the 100 again, and then everything else down to the 0 mark. We'll just run all of it. All right. So we'll run the 100, the 80, the 60, the 40, the 20, the 10, then the 8, 6, whatever they are, 4, 2, 1, 0, everything in that table we will run. Now, going into this, I know that all of these standards, I'm going to question them. Is that really going to be a linear curve? Right? I mean, that's a really wide window from 0 all the way to 100 for AA and AE. So what will happen is that I will plot these concentrations, and I will use the absorbances from the machine, and I will put that into an Excel spreadsheet so that way it can graph it for me. I want to see, is that linear? Yes or no? I don't know if it is or not. After this, we're going to run a few samples, and I'm just going to put here checks. Now, I'll talk and elaborate more about this in just a minute, but there will be a few samples that have been prepared that we will run along with our standards. So that way we can see, how is this machine running? I mean, is this like legitimate? Like, can we actually run 0 to 100 and get really good values? That's what this first half is all about. All right. Next up, we're going to reset everything after we run what we're supposed to run. We're going to reset all of it. And then we are going to go back in and create a new method, choose sodium again, choose the emission again. And this time we are going to set our high standard, not at 100 this time, but we're going to set our high standard at 10. And what will happen is that this will make the machine run a 1 absorbance at a 10 part per million. And here's why. That's a really wide window that we did first. So we're going to chop it down, and we're only going to focus on the lower concentrations here, 10 and lower. So we're resetting the machine. The 10 gets pumped in. The detector looks at that 10, and it scales itself up or it scales itself down. And it says, I'm going to make this a 1 absorbance for you. So that way, if you have something a little bit greater than 10, not a big deal. Something lower than 10 is preferable. It will be lower than 1. That is our working range of the absorbance values. So in a sense, I am making my detector not as sensitive, I guess, in a way, but really, truly, we are making it sensitive because it can see the 10 ppms, and it can do this job even better because it is scaling itself to the 1 absorbance with a 10 ppm solution. So I don't want you to think that we are gerrymandering anything in the instrument or anything in the software by doing this. What you need to understand is that in the emission world, it's got nothing to go off of. It's got no bulb to set itself first. And it uses the highest standard that you are preparing for your lab procedure, and it scales that highest standard to a 1 absorbance. That is how emission works, and that's how that's a little bit different than the absorption. Once we set this high standard, and in this case at a 10 ppm with a 1 absorbance, then what will happen here, I guess this is step 3, and then what will happen in the next step is that we will run 10 again as a sample, and we hope that's close to 1, right? And then we will go all the way down until we go back to 0. So we will generate a new graph here, and that new graph will also be very similar to the top one. So our concentrations will be on the X, and then our absorbances will be on the Y. And we hope that these things will make a linear graph. That's the whole point in doing this exercise, looking at emission and then looking at how our numbers are affected depending on what we do with it. Just as before, once we set that and once we run all of our standards, then we will have a series of checks that we will have to run along with those standards. So some of these will be things that maybe you prep, or there'll be things that we will prep, and we'll put that number into the spreadsheet and allow you to kind of solve for some errors and to look at how the instrument is performing. All right, so that's what 3 and 3 are going to say. Set the 100 ppm to read a 1 and read everything, and then set the 10 ppm to read a 1 and then read everything. There are 2 unknowns that you will be getting in the lab. Here is unknown number 1 and unknown number 2. They both get ran on the large window of standards. Number 3, it will only be unknown number 2. That is it. Unknown number 1 is really just too strong for us to do anything with. It doesn't going to make any sense. So we shorten that down for you, and we allow you to run unknown number 2, and that's it. I could get crazy, and I could add unknown number 1 back into this just to prove a point. If I do, you'll see that on your data sheet. You'll see that into Excel, just to keep it maybe consistent, and that way you can see what's happening to the errors as we process these samples if you're not very careful. Okay. Next up, we also need to run a quality check, and we just talked about the math of how to calculate the concentration there. The quality check will be ran on the high one. So the high standard, everything included, gets the unknown number 1, unknown number 2, and a quality check. With the lower standard window range for our 10 to 0, then it's only unknown number 2, and that is it. Everything else is going to be higher, unless, again, I tell you that unknown number 1 and a QC is going to be involved there. And then in these directions, it's also going to say, okay, listen, now that you have done this, why don't you use the data that you have gotten from the 0 to 100, that data, that original data, the very first run that you did, let's just focus on the 10 to 100. Let's pretend like you didn't read the 8 and the 6 and the 4 and the 2 and the 1 and the 0. Let's just leave those out. So what would happen to your graph if you plotted only 10 to 100 and only those absorbances? Does it make that graph more linear? Does it affect your numbers in any way, in any form or fashion? You know, just again, a different look on the data and the perspective of the AE instrument, and that is it. All right. Here's a data table. The data table is going to kind of somewhat keep you organized. It's just all about the readings, but our machines will print off reports, so you'll have that and you won't necessarily have to actually record any of those numbers down. Here's a spreadsheet example of what you will find in atomic absorption. This just gives you an idea of what we're working toward. So here is the data table, and this is the original standard prep. So how many meals did it take to make all of these? So the Excel spreadsheet is going to get you to calculate those yourself. And you want to enter those into the spreadsheet up at the top. You might not have made them, but I still want you to figure out how they would have been calculated. So if you did have to make them all, you know what volumes to use. Down here, it says standard curve for all the values. So the 100 to the 0 and the absorbance values that come from the instrument based on that. Notice the 100 is not a 1.0000, and that's because it uses the 100 as a guidance in order to get it close to 1 absorbance. And then when we rerun the 100, it's going to be close to 1, but it will be slightly under or slightly over, and that's okay. We understand that that's going to happen. So that's why that 100 is not a perfect 1.0000. So I'm going to plot those numbers, and I'm going to generate a calibration curve. And as you can expect, it really isn't linear at all. I mean, look at that. There is strong curvature that happens with those data points. And this gives me an idea that atomic emission cannot be used on just whatever concentrations that I want to run or that I want to use. Here's the standard curve for the high values. So this chops off all the lower ones, and it really only plots 10 to 100 now based on the same set of data. So the same report as above, but you just leave off the lower concentrations here. So look at what happens to our graph. I think it cleans up a little bit. It becomes in a way more linear, and the numbers might be a little more reliable. And then we go to our standard curve, and this is where we rescaled and reset the machine to make it read 10 as the 1 absorbance, and then from that we read everything else. Again, your data might look like the 3 graphs that you see on the screen, and that's because we are relying that this person did it the proper way, and maybe they didn't. But there's the graph for 10 and lower. So again, it's all about linearity. How close of a line is it going to be? And then how is it going to affect my concentrations when I begin to solve them in samples and unknowns? Up here underneath the QC sample preparation, you probably will not make this on your own. One person will make this, or I will make this. Somebody will be making it, and we will go ahead and record down the actual masses that we used to make it with, so that way you can do these calculations up here at the very top. Again, these are the calculations we walked through by hand, and you get Excel to do those calculations for you in that section. And then down here with each one of these graphs, you're going to see unknowns and QCs. So unknowns will be ran along with your standards. Those absorbance values will be plugged into the regression lines that get generated. So you're going to assume they are linear. Go ahead and do a linear regression line. Do a y equals mx plus b, and do what we've always done. Take the absorbance and plug it in for x and solve for y. Take the absorbance, plug it in for y, and solve for x. I'm sorry, you solve for x for concentration. I know they're not linear, right? We can see that graphically, but this is kind of what we've always done, and this is what we're going to do in this experiment as well. So you'll calculate the part per millions of each one of these, and we will give you the actual values so you can calculate error at some point in time. The same way with our high values, again, we're chopping off the lower ends here. And when the lower ends get chopped off, we get a new regression line. and that regression line is going to be used just as before, and we take our absorbance values and we plug them in for y and solve for x just like we did before. Finally, down here for the low ones, well, we just run 1, and that's unknown number 2. Unless I tell you otherwise, it could be unknown number 1 and the QC as well. But again, I'll tell you, I'll let you know. But we will do the same. So you plot your points, you generate a linear regression curve. Whatever y equals mx plus b shows up, that's what you will use. And plug your absorbances in for that and solve for x. That's what we'll do there. All right. Just as before, we solve for errors, and you need to know actual concentrations before you calculate errors. And we'll give you those after the lab is over. All right. So that's what this lab experiment is all about. It's just atomic emission, not absorbance. It's plotting them in different ways to see how these concentrations are affecting the lines, because some of them will not be linear, as you've seen from one of those examples. And how can we manage these standards to get something a little bit more linear, but also a working range with sodium in order for us to get really legit good numbers as far as data goes. All right, a couple of questions here toward the end. Again, those are going to get cleaned up. You might not see as many, but it will just be a summary of what we did and what you found and percent errors and that kind of thing. But a lot of that is actually on the Excel spreadsheet. So there is a chance that those pages will be shortened over the course of time, depending on when you've watched this video. But that's really all there is to atomic emission. So just setting the machine up, finding a emission line that's coming from the flame and the atoms, not necessarily the lamp. Working with calibration curves, finding linearities of these standards, trying to figure out what works the best, and then solving for a few unknown samples that we've made in-house that we're just basically providing to you. All right, so good luck in the lab. If you got questions, let me know. Good luck on the pre and post lab, probably quiz that comes along with this. And, you know, if you got questions, you know where to find me. See you then.